Okay, so we're moving to chapter 15 in Thomas Calculus, which is talking about multiple integrals. Of course, you're familiar with the single integrals that you have studied, and you have used single integration for finding areas between a curve and the x-axis, between two curves, finding the length of a curve, and so on. So you are already familiar with how to find the single integration. Here we're talking about multiple integrals and moving towards knowing what is double integration. Double integration in general, it's used, one of the applications of double integration is the finding of a volume. In general, when we are working in three-dimensional space, we have got objects and we can find the volume of those objects. The first part, 15.1, here we are talking about regions of rectangular form. What does that mean? When I say we are using regions of rectangular form, that means the objects that we are trying to find their volume, their bases are in rectangular form. Because when we're finding volume, if you remember, volume is equal to what? Area of base, okay? Area of base multiplied to what? Multiplied to the height. So the base that we have got here in 15.1, we're focusing on rectangular bases. When we have got rectangular bases, so we have got x is a number that's between two different numbers a and b, and y, the value of y is between c and d. In general, we are finding volume depending on, or let me say, using Fubini's theorem, which states that if we have got a function and that function is continuous throughout the rectangular region, which is the base of the object that we have got, where x is between a and b and y is between c and d. For finding the volume, when we have got f is continuous, we are simply saying that double integration of the f that we have got over the region R. Okay, that region R is the region that is here, the rectangular form. So that dA represents dx dy or dy dx. It changes from an example to another one, from a case to another one, whether in general I'm talking about double integration, whether you start to your integration with dx dy, you solve a dx dy, or you're changing the order to dy dx. It depends on the type of the functions that will be given to you, on the cases that you are in, the regions that we are on. So it is different from a case to another. Here, let's start with the first example. It says calculate the double integration of the function f over the region that is given to you, where f is equal to 100 minus 6x squared over the region that is given in here. So in this example, it's required from us to find the double integration, okay, over the region R for the function that we have got, okay, dA. Here in that first example, we will solve it both of the ways, dx dy and dy dx, to see the difference between them. And later on, you will be free when it's required from you to find the volume. You can use either way, or if you are obliged, you can use. You have to use the way that you are obliged to use. So now we are doing the solution. First, we are using the case where we have got double integration for the function 100 minus 6x squared y dx dy. Okay, since dx is here, so we are doing the inner integration first. So for the inner integration, I'm writing the bounds of the x. The outer integration is dy, so it is with respect to y, and we are using, or we are writing the bounds of the y here for the outer integration. The integration that is done in here, okay, this one, first we are doing it the same way that you have already known integration. So that one is equal to integration of -1 and 1. We are not changing anything with the y yet. And the inner integration with respect to x, it becomes 100x minus 6x to the power of 3 over 3 y, and this integration is from 0 to 2. And the dy, we haven't changed anything from it. Putting 2 and the 0 into that equation, what will we get? We will get that's equal to from -1 to 1. This inner integration that we have solved, it changes to 200 minus 16y when we are inputting the 2 and the 0 inside it, okay? And this is dy. Now we are done with the inner integration. Only the outer integration with respect to y is left to be done, and then we will be finding the volume of this function. Now finding the integration with respect to y gives me 200y minus 16y squared over 2, and this one runs from from -1 to 1. Inputting this -1 and 1 into that function that we have got gives us the volume equal to 400. So this is how we calculate double integration if the inner integration is with respect to x. Now we are doing it with respect to y first and then x. So if I have got integral, double integration of the function 100 minus 6x squared y, this time I will write dy dx. Of course, the result of those two integrations must be exactly the same. The inner integration is with respect to y. Since it's with respect to y, so I'm writing the bounds of y first. The outer integration is with respect to x, so I'm writing the bounds of x to the outer integration. Now we are solving the inside integration, which is with respect to y this time, okay? So we are solving this one. This equals to what? The outer remains the same. We are not changing anything from it. And the inner one with respect to y becomes 100y minus 6x squared y squared over 2. And the integration runs from -1 to 1 with dx remaining unchanged. Now put 1 and -1 into that equation. We get that this one changed to 0 to 2. Here we get 200. Okay, when we solve it, we get 200, simplifying it, and here we get dx. We have got dx. Taking this integration with respect to x, we get 200x, and the integration runs from 0 to 2. Plugging in 2 and 0 into that function, we get the result is 400, which is exactly the same result as we got from the previous one. So solving the integration dx dy or changing the order dy dx must give you the same solution. Moving to the second example, it says find the volume of the region that is bounded above by the elliptical paraboloid z that's equal to 10 plus x squared plus 3y squared, and below by the rectangle, this one. That means the base is a rectangle, and the rectangle, the x runs from 0 to 1, and the y runs from y to 2. Y runs from 0 to 2. We are solving this integration with respect to y first, and then with respect to x. So here, the example that we have got the integral of z. First we are writing the function, the integrand, 3y squared, and then with respect to y, in which we have to write the boundaries for the inner integration as 0 and 2, and then with respect to x, and the outer integration is 0 and 1. As usual, we're first solving the inner integration, and then we are solving the outer integration. So the outer integration is from 0 to 1. We are not changing it. Inner integration with respect to y becomes 10y plus x squared y plus 3y to the power of 3 over 3. That gives only, simplifies to y to the power of 3. And this integration that we solved runs from 0 to 2, and dx remains unchanged. Inputting the 2 and 0 into that function, then that integration gives me what? Of course, 0 and 1 remains the same, and the inside of the integration becomes 20 plus 2x squared plus 8 and dx. Okay, now we are taking the integral of this one with respect to x, so that gives me 20x plus 2x to the power of 3 over 3, so it gives me 2 over 3x to the power of 3 plus 8x, and the integration runs from 0 to 1. When we plug in 1 and 0 into that function, it gives us 86 over 3. So the volume under this function over the base 0, 1, 0, 2 is giving me 86 over 3. Of course, when you're solving this integration, finding this volume, let me write it with respect to x first. If you write it like that, 10 plus x squared plus first dx, then dy, where the inner integration runs from 0 to 1 and the outer integration becomes 0 to 2. If you solve this integration, it must again give you 86 over 3. But first you are integrating it with respect to x, then with respect to y. So this is all about section 1 of chapter 15. It's only simple integration and the application of integration, double integration, for finding volumes of objects which are rectangular in base.